Welcome to the fourth lecture on computational commutative algebra. First, we look at products of ideals. So we are continuing our discussion of operations on ideals. Let I1 through In be ideals of R. The product ideal is the R ideal generated by the set A1 times A2 times AN such that AI is inside II for all I. So from each one of these ideals, each one of the ideals in this family, take one element, A1 from I1, A2 from I2 and so on, take the product and do this for all possible choices. This gives us only a set, not an ideal, and look at the ideal generated by that thing. And this is denoted, the product ideal is denoted by the product . So just one remark. Suppose GI inside II is a generating set. This is true, I mean, for all I. For each ideal, take a generating set. Then we don't need to take, so in this thing here, we said take one element at a time from each in the family of the ideal and then take the product. So we don't need to take from all of them, we just need to take a product of elements from here where AI is in the generating set for each, okay, also generates the product. That's because if you have an element from an arbitrary element from II, then one can express it in terms of the elements from the generating set for II, and then one can rewrite it in terms of these. Okay, so this is the remark and a definition here. For m greater than or equal to 1, define the mth power of the product of I with itself m times, okay, and this is the mth power of So let's look at a couple of examples. So R is a ring, two variables, I is ideal generated by x cubed and y, and j is ideal generated by x squared and y squared. Okay. Sorry, the two. Okay. Then we take the product I times j. Okay. Then at that point we'll realize that we have not obtained the minimal generators. And then we are also asked to intersect these two, and let's see why that's relevant. Okay. So again I just show you the output that's relevant. I times j is the ideal generated by x to the 5. Okay, so that's just, so what it has done is taken this generating set and then multiplying them element by element. So x cubed times x squared, x cubed times y squared, okay, then y times x squared, and then y times y squared. This is a square. So we get this product, and it says it's an ideal of R. then when we look at this thing, we see that x square y already divides this thing. So anything that is a multiple of this is already a multiple of this one. So this is not relevant. It's a redundant generator. So we ask Macaulay to compute it using the mingens command. It outputs as a matrix. Again, we don't need to worry about these issues now. So y cube is necessary. One does not need x square y is necessary. X to the 5 is necessary, but as you observed, this is unnecessary. So it remove that thing. Then we ask, take the intersection of these two ideals, I and j. Okay. So notice that, so just a remark. Okay. So if you have a family of ideals, not necessarily finite, not necessarily finite family, then if you take the intersection is an ideal. Okay. Now suppose we just had I1 through In. Okay. Say this is ideals. And then if you take the product, this is inside Ij for every j. Therefore, the product of an ideal is always inside the intersection of the ideals. And what we were checking in this example is what's the relation between these two things. So the product ideal is generated by y cube, x squared y, and x to the 5th, while the intersection, and again at this point we just know that Macaulay 2 can compute an intersection, not exactly how it is done. The intersection of this ideal is y squared, x squared y, and x cube, and this is bigger than that because y square is in the intersection but not in the product, and similarly x cube is in the intersection but not in the product. So in general the intersection could be bigger than the product, but they are both relevant. I mean, they're okay. So now we have done with basic definitions about rings and ideals, and now we look at an important class of rings called Noetherian rings. Okay, so this is going to be a somewhat longish section on Noetherian rings. Okay, so definition. A ring, commutative ring, we said that hereafter when we say ring we mean commutative ring. R is said to be Noetherian if every ideal is finitely generated. Okay. So it's not our first examples that we know are Noetherian rings, which is why this is we have not yet come across a non-Noetherian ring. Of course, we have seen rings which we have not yet proved is Noetherian, but so far we have not seen any non-Noetherian ring. For example, fields are Noetherian. Why? A field has only two ideals, 0 and the full ring. The 0 ideal is generated by singleton 0, and the full ring is generated by the singleton 1 or any invertible element. So hence fields are Noetherian. PIDs, so for example, integers, k adjoint one single variable where k is a field, are Noetherian. That is, well, every ideal is principal, so it is finitely generated. Okay. Sorry, when you say finitely generated, it means that it has a finite generating set. We already saw the notion of a generating set, and now we are saying that an ideal has a generating set, which is a finite set. Okay. So this is also that we have seen. So here is one more observation which we will keep using. If R is Noetherian, then so is R mod I for every R ideal I. So the property of being Noetherian is transferred to the quotient rings. Okay. So we are interested not just in Noetherian rings or rings in general, but also about their morphisms, homomorphisms. Sorry, before that, before I discuss maps, let me just do a proposition. Okay. Let R be a R ring. Okay. Then the following are equivalent. Okay. The following are equivalent. 1. R is Noetherian. In other words, every ideal is finitely generated. 2. Every ascending chain of ideals So what do I mean by an ascending chain? I1 inside I2 inside I3 and so on. So it's a chain ascending by inclusion, stabilizes. That is, there exists an M such that for all n greater than or equal to M, the nth ideal is same as the mth ideal. So after a while, it's the same ideal that repeats ad infinitum. And let's look at the third condition. Every non-empty family of ideals has a maximal element. So just a maximal element in that family, not necessarily a maximal ideal, but a family has a maximal element. So this is the proof of this. It's not very difficult. So I leave that. I will sketch the steps in the proof in the exercises. And just condition 2, which says that every ascending chain of ideal stabilizes, is often referred to as ascending chain condition. In other words, sometimes A, C, C on ideals. So we say, a Noetherian ring is characterized by this ascending chain condition on ideals. Okay, proof will be done in the exercise. Okay, so now we want to talk about homomorphisms definition. By an R algebra, we mean a ring S together with a ring map from R to S. So what makes S an R algebra is the specification of a ring map. Okay, so for example, R is a ring to a polynomial ring. Okay. So this is, so here this goes to the constant polynomial. Okay. So the polynomial ring, this is an R algebra. Okay. Another example. Suppose we have two fields, of an extension of fields. Then K is an F algebra. Okay. And here is this map, here is a usual inclusion map. And a remark is that if S is an R algebra and T is an S algebra, this implies that T is an R algebra in a natural way. And what is that? So we are it's a ring. What we need to specify is a ring map from R to T, and for that take the ring map R2, the composite map. Okay, take the composite. Okay, so that makes T an R algebra. Now we come to an important definition in the while we for the study of Noetherian rings. Let S be an R algebra. Okay. Say that S is finitely generated. Say that S is a finitely generated R algebra. Or an R algebra of finite type. If there exists finitely many elements inside S, such that for every S in S there exists a polynomial in n variables such that if you take F, okay, so I apologize, I forgot a piece of notation. And what is it? So when we say S is an R algebra, it comes with the information about a ring map from R to S. Often we will not label it or we will not need it, but here we do. So let me just add that somewhere. And let's say that, or maybe I should just write, such that phi of F applied to S1 through Sn, this is S is equal to this, okay, where phi is the ring map, which is the ring map that makes S an R algebra. Sorry, I should have said this as part of the setup itself. So let me just reread this. So S is an R algebra. So to say it's an R algebra, it has to be a ring and there must be a ring homomorphism from R to S, and call that thing phi. Now say that S is finitely generated R algebra, or it's an R algebra of finite type if there are some finitely many elements inside S such that for every element of S there is a polynomial. So what does this mean? Phi of F. Okay. Here phi of F of x1 through xn is, okay, sorry, I will write it in. Okay. Suppose f of x1 through xn is some alpha is an n tuple, x1 to the alpha 1 through xn to the alpha n. So alpha is the n tuple which so this is a polynomial. This is a polynomial. So the coefficients are from the ring. Coefficient corresponds to that monomial. So then R alpha equals 0 for all but finitely many. Alpha. Okay. So that one can write like this. So then phi of f is the same polynomial, but except the coefficients are now substituted inside R, inside S. Okay. So let's go back here. So what we are saying is, for any element of S, there is a polynomial, which if you evaluate on these S1 through Sn will give S. But to make sense of it, this must be a polynomial, not with coefficients inside R, but coefficients inside S, and this is how it is made sense. That the coefficients themselves are just substituted through phi. Okay. So this is what we mean by a finitely generated algebra. And here is a remark, which I will sketch in the exercises. S is finitely generated. So we have to write finitely generated a lot in these notes. So Fg denote is whether it's an algebra or it's a ideal or later modules. F is for finitely generated. So you have to write that a lot. So okay, S is a finitely generated R algebra if and only if there exist x1 through xn variables and a surjective ring homomorphism from the polynomial ring in that many variables to S. Okay. So this is not at all very difficult to prove. Okay. So I'll describe one observation that we will need, but the point is that whatever was used in the definition, just plug it in. So I'll give one direction. So if you use that as the definition, it will give the direction from the top to bottom. And for the other direction, assuming this is true, that is true. So for that we need the following observation. Okay. Suppose we have S finitely generated R algebra and T a finitely generated S algebra. This implies that T is a finitely generated R algebra. So this is one observation that we need. We don't. So okay, the second observation that one can use is okay, S finitely generated R algebra and J an ideal of S. Okay, then S mod J is a finitely generated R algebra. Okay. So using observation 2, one can prove the other direction, which is, so this is finitely generated because the generating set are the variables. S is a quotient, so it is going to be a polynomial, this finitely generated thing modulo an ideal, and hence the quotient is also finitely generated. Okay, so observation 2 can be used to prove the remark earlier. And observation 1 is more general. In fact, it is better to prove the remark earlier and then prove observation 1. Okay. Okay, so here now we come to one of the most important basic theorems in commutative algebra, called the Hilbert Basis theorem. Okay, so what is the statement of the theorem? R Noetherian, S finitely generated R algebra, then S is Noetherian. And we will look at in these exercises. So, for example, exercises one will be able to show a non-Noetherian ring now, okay, which I will do it in the exercise. Okay. So now I want to give we are not going to prove it now, but I would like to give some general discussion about this remarks, which using which we will reduce it to some apparently special cases, but which it is not. Okay. So that's what I will do now. Okay. So general remarks. Okay. So we know that R is, so this is the hypothesis. We are not discussing the Noetherian S finitely generated R algebra. Okay. We want to show that S is Noetherian. So then write S as some polynomial ring. This was the remark earlier, where J is an ideal of that. Okay. J is an ideal of that ring, of the polynomial ring. To show that S is Noetherian, it is enough to show that the polynomial ring is Noetherian. We noticed earlier that quotients of Noetherian rings are Noetherian. Okay. This we can do on the number of variables. That is because a polynomial ring in n variables is isomorphic as a ring to a polynomial ring in n minus 1 variables first and then the last variable. And by induction, if we know this is Noetherian, and then by induction again one variable case we can prove, then we know that this is true. Okay. So then we can restate the theorem to the following. We just have to prove it for one variable. So we start from an arbitrary finitely generated thing, from which we said, okay, we just have to do for polynomial rings, and then we do induction and say we just have to do one variable. Okay. So this is equivalent to the general version of Hilbert Basis theorem that we stated earlier, because if we can prove this, we can go back. Okay. So this we will not prove, partly because we would like to become familiar with the different proof, which works only for fields. I'll clarify in a minute, but for computational purposes, that's on one case it's more than enough. Secondly, actually more importantly, it gives us it introduces us to some of the basic concepts of computational commutative algebra. So in fact, this proof is much simpler, much shorter. The other proof is somewhat longer, but it introduces us to newer notions and things that are geared towards understanding computational commutative algebra. So we'll only prove that special case. Okay, so for a proof of this is proved in this generality in Eisenberg's book, which I mentioned in the first first lecture, Commutative Algebra with a View Towards Algebraic Geometry, okay, Chapter 1, Section 1.4. In this generality, okay, it is proved there. So it will be an exercise for you to read the proof and understand it. Okay. So I'll just say what we are going to do now and in this lecture. Okay. So we will prove a special case, okay, which is that K field and let's say S is a finitely generated K algebra, then S is Noetherian. Okay. And arguing as earlier, S can be written as a quotient of a polynomial ring over K. So again, it's enough to show that R, which is a polynomial ring in n variables for arbitrary n, finite, is Noetherian. Okay. And in proving this, we are following the book by Cox, Little and O'Shea, which okay. And it's not, it's spread in a few sections, and we will go over this proof carefully. Partly, our motivation is to understand the points relevant to computational questions. Okay. So this is the end of this lecture, and we will continue with the developing the ideas to prove this theorem from the next lecture.